There is a quiet fear that most people never talk about. Not the fear of darkness, not even the fear of being alone, but the fear that something enormous could disappear and nobody would notice, because in the universe things normally leave evidence. When a star dies, it explodes. When galaxies collide, the sky lights up with billions of new stars. When black holes feed, space screams with radiation that telescopes can detect across the universe. The cosmos is noisy, violent, chaotic, and yet astronomers found a place where something very strange happened. A place where thousands of galaxies should exist, but do not. A region so huge that light itself needs more than 300 million years just to cross it. Inside that space, scientists expected to find around 10,000 galaxies. Instead, they found almost nothing. Not faint galaxies, not hidden galaxies, just emptiness. A hole in the structure of the universe itself. Astronomers call it the Boötes Void. And the deeper scientists studied it, the more uncomfortable the question became. Where did those galaxies go? To understand why the Boötes Void is so unsettling, you have to forget the way most people imagine space. Many people think galaxies are scattered randomly across the universe, like grains of sand on a beach. But that picture is completely wrong. If you could travel far enough away to see the universe from a distance, the pattern would shock you. Galaxies are organized. They form enormous filaments stretching across space for hundreds of millions of light years. These filaments connect to each other, forming something scientists call the cosmic web. Between those glowing filaments are giant bubbles of emptiness called voids. Imagine soap bubbles pressed together. The thin walls between the bubbles hold most of the material. The centers remain mostly empty, but here is the key detail. Even normal voids are not truly empty. A typical cosmic void still contains hundreds, sometimes thousands of galaxies drifting far apart from each other. The Boötes Void breaks that rule. This region is enormous, about 330 million light years across. To picture that size, imagine traveling at the speed of light, the fastest speed anything can move. Even then, it would take 330 million years to cross from one side of this region to the other. Inside that gigantic volume of space, astronomers expected to find thousands of galaxies. Instead, they found fewer than 100. The discovery happened in the early 1980s when astronomer Robert Kirshner and researchers at the Harvard-Smithsonian Center for Astrophysics were mapping galaxy distances using redshift surveys. Redshift is how astronomers measure distance in the universe. As space expands, light from distant galaxies stretches toward the red side of the spectrum. The farther away a galaxy is, the more its light shifts toward red. By measuring that shift, scientists can map where galaxies sit in three-dimensional space. When Kirshner's team plotted those galaxies on their maps, something strange appeared. A huge gap, a massive hole where galaxies should exist. At first, the researchers assumed the data had to be incomplete. Maybe telescopes had simply missed galaxies in that direction. But as more surveys arrived, using better instruments and larger telescopes, the same result kept appearing. The Boötes Void was real. Before we go deeper into this strange place, there is something worth mentioning. Investigations like this take time. They involve digging through telescope records, scientific papers, and decades of astronomical research. If you enjoy these kinds of deep space investigations, consider subscribing. It helps support this kind of long-form research into the unknown. Now here is where things start getting strange. Because the Boötes Void is not just empty. It is too empty. And that single fact has been confusing scientists for more than 40 years. In order to understand what makes this void so strange, astronomers had to map the universe on a much larger scale than ever before. One of the most important projects was the Sloan Digital Sky Survey. This survey measured the positions and distances of millions of galaxies. When scientists plotted all those galaxies together, the structure of the universe finally became visible, and it did not look random. The map revealed enormous filaments of galaxies forming long glowing chains across space. These chains connected to clusters containing thousands of galaxies packed tightly together. Between those structures were huge empty regions, voids. When astronomers zoomed out even farther, the universe began to resemble foam, or the structure of a sponge, bright filaments surrounding hollow spaces. Inside most voids, astronomers still find galaxies scattered across the darkness. But when they examined the Boötes region using telescopes like those at Kitt Peak National Observatory and later the Keck Observatory in Hawaii, something unexpected happened. They found almost nothing. Follow-up observations using the Hubble Space Telescope spectrograph confirmed the distances of the few galaxies inside the void. Radio observations from the Arecibo Observatory detected faint hydrogen signals from several of them before the telescope collapsed in 2020. And every observation told the same story. The void contained only about 60 galaxies. 60, where there should be thousands. Those galaxies drift through space like lonely islands surrounded by a dark ocean. Each one sits hundreds of millions of light years away from its nearest neighbor. If intelligent life existed inside one of those galaxies, their night sky would look terrifyingly empty. No glowing clusters nearby, no nearby galaxies. Just darkness stretching across unimaginable distances. But the edges of the Boötes Void look very different. Around the boundary of the void, galaxies gather into enormous walls and clusters. One of these regions connects with the Hercules supercluster, where galaxies pack together in huge gravitational communities. When astronomers studied these boundaries, they noticed something that looked almost deliberate. It appeared as if matter had been pushed outward from the center, almost like crumbs being swept to the edge of a table. That observation started a quiet debate among cosmologists because it raised a strange possibility. Maybe nothing vanished from the Boötes Void. Maybe the galaxies were simply pushed away. And if that happened, something must have pushed them. Something powerful enough to move entire galaxies across millions of light years. If galaxies were pushed away from the center of the Boötes Void, something enormous must have caused it. Not a single star, not even a black hole. We are talking about forces acting across hundreds of millions of light years. That scale is so large that only a few things in the universe could possibly influence it. Gravity, dark matter, and the expansion of space itself. To investigate this, astronomers began running simulations of the universe using powerful supercomputers. Teams at NASA's Jet Propulsion Laboratory, the Max Planck Institute for Astrophysics, and research groups connected to the European Southern Observatory started testing different models of cosmic evolution. They built digital universes. Inside those simulations, they recreated the early moments after the Big Bang. Tiny variations in matter density were added to the model. Some areas began slightly denser than others. Gravity slowly amplified those differences. Denser regions pulled more matter inward. Galaxies formed. Clusters appeared. Filaments stretched across space. Between those filaments, empty regions began forming. Voids. The longer the simulation ran, the larger the voids became. Matter slowly drained out of them, pulled toward the surrounding filaments. At first, this looked promising. Maybe the Boötes Void was simply an extreme version of that normal cosmic process. But when scientists compared the simulations with real observations, something still did not match. Even the largest simulated voids still contained far more galaxies than the Boötes region actually does. The models predicted hundreds. The real universe showed only a few dozen. The gap between prediction and reality was huge. That meant something about the Boötes Void was different from what standard models expected. Astronomers started examining the edges of the void more carefully. Using deep field observations from the Keck Observatory and spectroscopic measurements gathered through Hubble telescope records, they measured the movement of galaxies around the boundaries. What they found was interesting. Many of those galaxies appear to be slowly drifting away from the center of the void. Not quickly, not violently, but steadily, almost as if gravity from surrounding structures has been pulling them outward for billions of years. Imagine a valley surrounded by mountains. Rainwater naturally flows down the slopes into the lowest point. Now imagine the opposite, a giant invisible hill forming in space. Everything around it slowly slides away. That idea led scientists to a concept called an underdense region. An underdense region means there was simply less matter in that area from the very beginning. Right after the Big Bang, the universe was not perfectly smooth. Tiny fluctuations existed everywhere. Some areas had slightly more matter, others had slightly less. Those small differences grew over time. Regions with extra matter collapsed into galaxies and clusters. Regions with less matter became emptier. Over billions of years, gravity exaggerated those differences. Voids expanded. Matter drained toward the edges. But here is where the Boötes Void becomes unsettling again. Even if the region started with less matter, the numbers still look extreme. Most cosmological models suggest that such a huge void should have broken apart or filled partially as surrounding structures evolved. Instead, the Boötes Void remained mostly empty, almost untouched, which forced astronomers to ask another question. Was something preventing galaxies from forming inside the void? To answer that, researchers turned to one of the most important ingredients in the universe: dark matter. Dark matter cannot be seen directly. It does not emit light, but it has gravity. And gravity shapes the universe. Galaxies form inside halos of dark matter. Without those halos, gas cannot collapse into stars. That means if the Boötes region lacked dark matter, galaxy formation would be extremely rare. Teams studying gravitational models used observations from large sky surveys and data connected to the Planck satellite mission to estimate dark matter distribution across cosmic structures. Their results hinted at something fascinating. The Boötes Void might contain far less dark matter than surrounding regions. If that is true, the void did not just lose galaxies, it might never have had the conditions needed to create them in the first place. But even that explanation leaves a strange detail behind, because a few galaxies do exist inside the void, and when astronomers studied them carefully, those galaxies showed unusual behavior. Using spectral data gathered at the Keck Observatory and radio signals recorded through Arecibo legacy data before the telescope collapsed, scientists measured the gas content inside several of those isolated galaxies. What they found was surprising. Many of those galaxies still contain huge amounts of hydrogen gas, more than galaxies in crowded regions. That means star formation inside them has been slow and steady for billions of years. In crowded parts of the universe, galaxies collide constantly. Mergers trigger bursts of star formation. But inside the void, nothing disturbs them. They evolve quietly, almost peacefully. Picture a busy city where buildings constantly rise and fall. Now compare that to a tiny village in the middle of a desert that remains unchanged for centuries. That is the difference between galaxies inside the void and galaxies in crowded cosmic neighborhoods. Yet even with that peaceful environment, the number of galaxies remains incredibly small. And that leads to a deeper puzzle. Because if the Boötes Void formed simply because of low matter density, the edges should gradually refill over billions of years. Gravity should slowly pull some galaxies back toward the center. But observations show the opposite trend. The void still appears to be expanding. The boundaries continue moving outward, almost like an invisible pressure pushing everything away. And that idea led scientists to consider something even stranger, a force acting not through gravity, but through the expansion of space itself. For a long time, astronomers believed gravity was the main architect of the universe. Gravity pulls things together. It gathers gas into stars, stars into galaxies, and galaxies into clusters. On the largest scales, gravity acts like a sculptor, slowly shaping the cosmic web. But toward the end of the 20th century, scientists discovered something unsettling. The universe is not only expanding, the expansion is accelerating. That discovery came from observations of distant supernova explosions. By measuring the brightness of these explosions, astronomers realized the universe was stretching faster and faster over time. Something was pushing space outward. That unknown force was given a simple name: dark energy. Dark energy now appears to make up nearly 70% of the universe. It is everywhere, filling space itself. And unlike gravity, which pulls matter together, dark energy pushes space apart. Normally, this effect is extremely subtle. On the scale of galaxies, or even clusters of galaxies, gravity still wins. But across billions of light years, dark energy slowly stretches the universe like an invisible tension pulling everything apart. Some cosmologists began wondering whether dark energy might play a role in shaping enormous cosmic voids. If a region of space already started slightly empty after the Big Bang, dark energy could amplify that emptiness over billions of years. Matter would slowly drift away toward denser regions where gravity dominates. Picture a giant sponge expanding underwater. The holes inside the sponge grow larger as the material stretches outward. In that picture, the Boötes Void might not be a missing piece of the universe. It might be a place where the stretching of space itself exaggerated an early imbalance. The result would be exactly what astronomers observe today, a massive bubble surrounded by dense walls of galaxies. But even this explanation has complications. Dark energy acts everywhere in the universe. If it were responsible for creating the Boötes Void alone, then similar voids should be extremely common. Astronomers do see many voids across cosmic maps, but most are smaller and contain far more galaxies. The Boötes Void still stands out as unusually extreme. To investigate further, scientists turned to the most detailed cosmic maps ever created. Projects like the Sloan Digital Sky Survey and later deep field surveys from the Hubble Space Telescope allowed astronomers to examine the distribution of galaxies across enormous distances. When these maps were analyzed, something fascinating appeared. The Boötes Void sits at the intersection of several giant structures in the cosmic web. Filaments of galaxies surround it like the edges of a giant cell. One of the most prominent neighboring regions is the Hercules supercluster area, where galaxies cluster together in dense formations. When researchers trace the motion of galaxies along these surrounding filaments, they noticed a pattern. Many of them appear to be drifting away from the void, not violently, not quickly, but steadily. The motion is slow enough that it takes billions of years to measure clearly, but the direction is consistent. Galaxies along the boundaries behave like leaves floating away from the center of a calm lake. This movement suggests the void is still evolving, still growing. And that realization changed how scientists thought about the structure of the universe. Voids are not static, they expand. As matter flows toward denser regions, the emptiest areas become even emptier. It is a slow process, unfolding over cosmic time. But the Boötes Void may represent one of the most extreme examples of this process ever observed. To understand it better, astronomers began examining the few galaxies that actually exist inside the void. These galaxies are unusual in several ways. First, they are incredibly isolated. The nearest neighboring galaxies are hundreds of millions of light years away. In cosmic terms, that distance is enormous. Second, many of these galaxies still contain large amounts of hydrogen gas. Hydrogen is the raw material for forming new stars. In crowded regions of the universe, galaxy collisions and gravitational interactions often trigger bursts of star formation. But those same interactions also strip gas away over time. Inside the void, those disturbances almost never occur. The galaxies evolve slowly, quietly. Some astronomers have compared them to ancient forests that grow undisturbed for centuries. Observations from the Keck Observatory have revealed that several of these galaxies show signs of steady star formation continuing even today. Radio measurements from the Arecibo legacy data also detected hydrogen gas clouds surrounding some of them. This tells scientists something important. Life inside a cosmic void is peaceful, but that peaceful environment comes with a strange consequence. Very few galaxies ever appear there. To visualize this, Imagine planting seeds across a field. In fertile soil, plants grow everywhere. But if a large patch of ground contains almost no nutrients, only a few plants will survive. The Boötes Void might be a cosmic version of that barren patch, a region where the ingredients needed to build galaxies were scarce from the beginning. But the puzzle still does not end there, because when astronomers calculate how matter should have flowed through the early universe, they still expect more galaxies than what we see. The numbers do not quite line up. Even the most refined simulations run at places like NASA's Jet Propulsion Laboratory struggle to reproduce a void this empty, which means something about the early history of that region might have been unusual. Some cosmologists have suggested that the Boötes Void could have formed from several smaller voids merging together. Over billions of years, neighboring bubbles of emptiness expanded until they collided and combined into a single enormous void. That process happens in simulations of cosmic structure. When two voids grow large enough, the thin filament of galaxies separating them can collapse. Once that boundary disappears, the two regions become one larger void. If that happened repeatedly in the Boötes region, the result could be a massive empty space like the one we see today. But even this idea leaves one haunting detail behind. If 10,000 galaxies were expected to form there originally, and if they were pushed outward over billions of years, where exactly did they go? Astronomers have searched the surrounding regions carefully. Many galaxies do appear along the edges of the void, yet the numbers still feel slightly off, as if the cosmic accounting does not quite balance. And that lingering uncertainty keeps the Boötes Void one of the strangest places in the observable universe, because the more scientists study it, the more it begins to look like a giant scar in the cosmic web, a place where the normal rules of structure formation stretched to their limits, a place where gravity, dark matter, and cosmic expansion all played their roles in shaping an enormous bubble of emptiness. But there is still one final idea that makes some researchers pause, an idea that pushes the imagination even further. What if the Boötes Void is not just a region where galaxies fail to form, but a place where the structure of the universe itself behaved differently for a brief moment in cosmic history, a moment when the balance between gravity and expansion tipped in a strange direction. And if that moment really happened, the Boötes Void may not just be an empty place, it might be evidence of how fragile the cosmic web truly is. If the universe were a perfectly smooth place, the Boötes Void would make no sense at all. Galaxies would form everywhere. Matter would spread evenly. The cosmic web would never appear. But the universe is not smooth. It began with tiny wrinkles. Right after the Big Bang, the universe was filled with a hot ocean of particles and radiation. Within that ocean were small differences in density. Some regions had slightly more matter than others. The differences were incredibly small, less than a fraction of a percent, yet those tiny imbalances shaped everything that came later. Evidence for these early wrinkles was captured by the Planck satellite when it mapped the cosmic microwave background. That faint glow is the leftover heat from the birth of the universe. When scientists studied those maps carefully, they saw the ancient pattern of fluctuations that later grew into galaxies and clusters. Think of it like a map of ripples frozen in time. Over billions of years, Gravity amplified those ripples. Regions with extra matter became seeds for galaxies. Regions with less matter became cosmic deserts. The Boötes Void may represent one of the largest deserts ever discovered. But even deserts usually contain some life. The strange part is how extreme this one became. To understand why, cosmologists looked at how matter moves across the cosmic web. Imagine standing on a hillside during heavy rain. Water flows downhill toward the lowest points. In the universe, matter behaves in a similar way. Gravity pulls it toward regions that already contain more mass. But when matter drains away from a region, the emptiness begins to grow. As the region becomes emptier, gravity there weakens. That allows surrounding structures to pull even more matter away. Over billions of years, this process can transform a slightly underdense region into a massive void. Computer models run with data from Sloan Digital Sky Survey. Maps suggest that once a void reaches a certain size, it begins expanding faster than surrounding space, not because it is exploding outward, but because there is simply less gravity inside it to slow down the expansion of the universe. This means the Boötes Void might actually be expanding faster than the rest of the cosmos around it. Galaxies near the edges slowly drift away from the center, like leaves, being pulled toward the outer rim of a whirlpool. This idea helps explain why the boundaries of the void appear so sharply defined. Observations from the Keck Observatory and distance measurements gathered through Hubble spectrograph records show that galaxies along the edges often form long sheets and filaments. These structures act like the walls of the cosmic bubble. Inside those walls, the emptiness continues growing, but there is still something about the Boötes Void that keeps scientists uneasy. When astronomers study the galaxies inside the void, they find that some of them look different from galaxies in crowded regions. Several of them are smaller, more fragile. Some appear stretched or distorted in unusual ways. Using deep imaging data gathered by the European Southern Observatory and spectroscopic analysis from Keck, researchers noticed that a few void galaxies show signs of isolation stretching back billions of years. These galaxies evolved without major collisions, without the constant gravitational tug-of-war that shapes most galaxies. In some cases, they still contain thick clouds of cold hydrogen gas. Radio observations collected through Arecibo legacy data revealed that several void galaxies possess enough gas to continue forming stars for billions of years. That might sound like a good thing, but it also highlights how strange their environment is. In crowded regions of the universe, galaxies interact constantly. Those interactions drive star formation, distort spiral arms, and sometimes trigger the growth of supermassive black holes. Inside the void, those events are rare. Galaxies live quiet lives, almost untouched by the cosmic drama happening elsewhere. To someone living in one of those galaxies, the universe would look very different. The night sky would contain almost no neighboring galaxies. Just distant points of light scattered across unimaginable darkness. Even the cosmic web itself would be nearly invisible, which leads to a strange thought. Most civilizations, if they existed in those galaxies, might never realize how vast the universe truly is. They might believe they live in a lonely cosmos with very little structure, because the nearest giant galaxy clusters would lie hundreds of millions of light years away, far beyond their ability to observe clearly. In a strange way, the Boötes Void reminds us how lucky we are. From Earth, we sit inside a rich cosmic neighborhood. The Milky Way belongs to a local group of galaxies. Beyond that lies the Virgo cluster, a massive gathering of thousands of galaxies. And beyond that, enormous filaments stretch across the cosmic web. We live in a busy intersection of the universe. But the Boötes Void is the opposite, a vast empty intersection where almost no traffic passes. Still, the central mystery remains. Even if matter drained away from this region over billions of years, the models still suggest more galaxies should have formed there. Something about the early conditions of the Boötes Void must have been unusual. Some cosmologists have proposed that the region may have originated from an exceptionally large underdensity in the early universe, a fluctuation far bigger than most others. If that fluctuation existed, it could have created a giant bubble that expanded rapidly as the universe evolved. That bubble would push matter outward. Galaxies forming nearby would drift toward the edges. Over time, the center would become almost completely empty. This explanation fits many of the observations, but it also raises another unsettling idea. If one such giant underdensity existed in the early universe, there could be others, hidden far beyond the regions we have mapped. Some might be even larger than the Boötes Void. In fact, modern galaxy surveys suggest that the cosmic web contains hundreds of thousands of voids of different sizes. Most are small, some are medium. A few are enormous, and the Boötes Void is one of the biggest we have ever discovered. But it may not be the largest. And that thought brings us to a strange possibility that some scientists have quietly discussed. The possibility that voids are not just empty spaces between galaxies. They might be clues to something deeper about the structure of the universe. Clues about how matter first gathered after the Big Bang. Clues about the behavior of dark matter and dark energy. And maybe even clues about the limits of our current cosmological models. Because when astronomers map the universe carefully enough, they start to notice something strange. The largest structures in the cosmos are not the galaxies, not even the clusters. The largest structures are the empty spaces between them. The Boötes Void is one of those enormous spaces, a cosmic silence stretching across hundreds of millions of light years. And the deeper we study it, the more it forces us to ask a question that still has no final answer. What does it really mean for part of the universe to be empty? And what if that emptiness is telling us something we have not yet fully understood? The deeper astronomers studied the Boötes Void, the more it began to feel less like a simple empty region and more like a clue, not a clue about a single galaxy or a single cluster, but a clue about the architecture of the entire universe. For a long time, scientists believed the largest meaningful structures in the cosmos were galaxy clusters. These enormous gatherings can contain thousands of galaxies bound together by gravity. The Virgo cluster near our Milky Way is one example, a crowded city of galaxies drifting through space together. But when surveys, like the Sloan Digital Sky Survey, expanded our cosmic maps, something bigger appeared. clusters were not isolated. They were connected. Filaments of galaxies stretched across space like glowing bridges linking cluster to cluster. Some of these filaments extended hundreds of millions of light years. When astronomers zoomed out far enough, they saw a gigantic network, the cosmic web. This web contains nearly all the matter in the observable universe. Galaxies form along its threads. Clusters sit at the intersections where several filaments meet, and between those threads lie enormous cavities, voids. At first glance, it might seem like these empty regions are simply leftovers, the spaces where matter never gathered. But modern cosmology suggests something more dynamic. Voids grow. As galaxies form along filaments, gravity pulls matter away from the emptiest regions. That process slowly drains those regions of material. The emptiness becomes stronger over time. It is a strange idea. In the universe, emptiness can expand, and the Boötes Void may be one of the most dramatic examples of that process. Observations gathered from the Keck Observatory and redshift surveys connected to the Harvard-Smithsonian Center for Astrophysics show that galaxies near the edges of the void often move outward from its center. The motion is subtle. It takes millions of years to notice the shift clearly, but the pattern suggests that the void behaves almost like a slowly inflating bubble. Everything near its center drifts away. Over billions of years, the result becomes enormous, a region hundreds of millions of light years across where almost no galaxies remain. But even with this explanation, a strange question continues to bother scientists. Why did the Boötes Void start so large? Cosmic simulations performed using data from the Planck satellite and large-scale models run through institutions like NASA's Jet Propulsion Laboratory attempt to recreate the universe from its earliest moments. These simulations begin with the faint ripples in density left behind after the Big Bang. Gravity then amplifies those ripples over time. In most simulations, voids form naturally, but few reach the extreme scale of the Boötes Void. That means the original density fluctuation in that region may have been unusually large. To picture this, imagine the early universe as a landscape filled with tiny hills and valleys. Galaxies form on the hills where matter gathers. Voids form in the valleys where matter is scarce. Most valleys are shallow, but the Boötes Void may have started as a deep valley in the density map of the early cosmos. Over billions of years, gravity pulled matter away from that valley and towards surrounding ridges. The valley grew deeper, the ridges grew higher. Eventually, the valley became the giant bubble we observe today. But here is where the story becomes even stranger. Some cosmologists have asked a question that sounds almost unsettling. What if the Boötes Void is not just a valley in the cosmic landscape? What if it is a boundary? A boundary between regions of the universe that formed slightly differently during the earliest moments after the Big Bang. This idea comes from theories about inflation. Inflation refers to a brief period immediately after the Big Bang when the universe expanded incredibly fast. During that tiny fraction of a second, space stretched faster than light. That rapid expansion could have amplified quantum fluctuations, turning microscopic differences into enormous cosmic structures. If inflation behaved slightly unevenly in different places, some regions might have ended up with much lower matter density than others. those regions would evolve into giant voids. Most of these voids would remain moderate in size, but a few might grow enormous. The Boötes Void might be one of those rare giants. If that idea is correct, the void is not simply empty space. It is a fossil from the earliest moment of cosmic history, a region where the initial conditions of the universe were slightly different, a place where the seeds of structure were weak from the very beginning, and over billions of years that tiny difference turned into one of the largest empty regions known. Yet even this explanation does not answer every question, because when astronomers look closely at the galaxies inside the void, they notice something intriguing. Some of them appear connected by faint filaments of gas and dark matter. These structures are extremely thin, so thin that detecting them requires careful analysis using deep surveys and spectroscopic measurements. Data from instruments connected to the European Southern Observatory and deep observations recorded by the Hubble Space Telescope suggest that the void may still contain faint threads of matter. These threads are like ghostly remnants of the cosmic web, almost invisible, but not entirely gone. If these faint structures exist, they might represent the final traces of the cosmic network that once stretched across this region. Over billions of years, gravity and expansion may have slowly drained those threads until only fragments remained. That idea leads to a haunting image. Imagine a giant spider web drifting in the wind. Slowly, strand by strand, parts of the web tear away. Eventually, only a few thin threads remain, barely visible in the sunlight. The Boötes Void might be what is left when most of a cosmic web cell dissolves, a place where structure once existed but gradually faded. But even with all these explanations, the Boötes Void still carries an eerie feeling. Because when astronomers map the universe, they realize something profound. The largest structures in existence are not galaxies, not clusters, not even superclusters. The largest structures are the empty spaces between them. Voids like Boötes dominate the volume of the universe. Galaxies are simply the bright foam floating along the edges. This realization changes the way we think about the cosmos. The universe is not mostly filled with matter. It is mostly filled with emptiness. And sometimes that emptiness gathers into places so large that they reshape our understanding of cosmic structure. The Boötes Void is one of those places. A giant, quiet region stretching across hundreds of millions of light years. A place where galaxies are rare and the cosmic web seems to break apart. But there is still one final possibility that scientists sometimes discuss quietly when studying voids like this. A possibility that sounds almost impossible at first. What if voids are not just regions where matter drained away? What if they are places where something prevented matter from ever gathering there in the first place? Something embedded in the earliest structure of space itself. Something that shaped the universe long before the first galaxy was born. And if that idea is even partly true, the Boötes Void might not just be an empty place. It might be a window into the earliest moment when the universe decided where galaxies would exist and where they would not. If the Boötes Void really traces back to the earliest moments of the universe, then the story does not begin with galaxies at all. It begins with a universe that was barely a few 100,000 years old. At that time, there were no stars, no galaxies, no planets, just a hot, expanding ocean of particles slowly cooling as space stretched outward. Eventually, the universe cooled enough for the first atoms to form. Light that had been trapped inside the hot plasma suddenly became free to travel. That ancient light still exists today. Astronomers call it the cosmic microwave background. It is the oldest light we can see, a faint glow filling every direction in the sky. When scientists studied that glow using spacecraft like the Planck satellite, they discovered something remarkable. The microwave background is not perfectly smooth. Tiny temperature variations appear across the sky. These variations represent slight differences in density that existed when the universe was still very young. Some regions had a little more matter, some had a little less. Those tiny differences were incredibly small, but gravity slowly amplified them over billions of years. Dense regions became galaxies. Less dense regions became voids. When researchers compared maps of those early fluctuations with the large-scale structure we see today, they noticed a connection. The cosmic web appears to follow patterns that were already present in the microwave background. The seeds of galaxies were planted almost immediately after the Big Bang, and the seeds of voids were planted at the same time. In that sense, the Boötes Void might have started as one of those early low-density regions. But for it to grow into something this large, the original fluctuation would have needed to be unusually strong. Picture the early universe like a sheet of fabric stretched tight. Most parts of the fabric are smooth, but in a few places, the fabric dips downward more deeply than the surrounding areas. Those deeper dips become the largest voids later in cosmic history. The Boötes region might have been one of the deepest dips in the entire cosmic landscape. Over billions of years, gravity pulled matter away from that dip and toward nearby filament. Galaxies gathered along the edges. The center grew emptier. The void expanded. But there is still something about the Boötes Void that continues to puzzle astronomers. When scientists map the positions of galaxies along the boundary, they notice that the surrounding structures are extremely prominent. Large walls of galaxies form a kind of shell around the void. These structures contain enormous amounts of mass. Clusters inside those walls sometimes contain thousands of galaxies bound together by gravity. The distribution almost looks like the rim of a giant bowl. Inside the bowl, space is nearly empty. Outside it, matter piles up in thick layers. Researchers studying the edges of the void using redshift surveys have noticed that the surrounding filaments appear unusually strong. This could mean that as matter drained from the center of the void, it collected along those boundaries, strengthening them over time. Think of pushing sand outward from the center of a table. The sand gathers around the edges. The middle becomes bare. That analogy works surprisingly well for the large-scale structure of the universe. Matter flows away from under-dense regions and accumulates where gravity is stronger. But the Boötes Void still feels extreme. Even with billions of years of cosmic evolution, such a vast empty space remains unusual. Some cosmologists have explored another idea. What if the Boötes Void is not simply the result of one underdense region growing over time? What if several smaller voids merge together? In simulations of cosmic structure, voids can collide and combine. As neighboring empty regions expand, the thin filaments separating them sometimes collapse. Once that happens, two voids merge into one larger cavity. If this process happened repeatedly in the Boötes region, the result could be a giant supervoid formed from many smaller ones. Over billions of years, these merged voids could clear out most of the galaxies from the interior. The few galaxies remaining today might simply be those that formed in isolated pockets where enough matter survived. This idea fits many of the observations, but it also raises a strange consequence. If voids merge and grow over time, the largest structures in the universe might not be clusters or superclusters. They might be the voids themselves. The empty spaces might actually dominate the architecture of the cosmos. And when astronomers measure the total volume of the observable universe, they see evidence for exactly that. Voids occupy most of the space between galaxies. Clusters and filaments contain the majority of the mass, but they take up a relatively small fraction of the total volume. In other words, the universe is mostly empty. And the Boötes Void is one of the most dramatic examples of that emptiness. Yet even with all these explanations, there is still a lingering curiosity. The Boötes Void feels almost too perfect, too round, too clean. Most voids have irregular shapes with ragged edges where filaments intrude. But the Boötes region appears unusually symmetrical. That symmetry has led some researchers to explore more speculative ideas. One possibility involves early cosmic bubbles formed during phase transitions shortly after the Big Bang. During those transitions, different regions of space might have briefly behaved differently before settling into the same physical laws we observe today. If a bubble of space formed with slightly lower matter density, it could expand and push matter outward. Over billions of years, that bubble might evolve into a massive void. Another possibility involves dark energy itself. If dark energy behaved slightly differently in the early universe, certain regions might have expanded faster than others. That accelerated expansion would prevent matter from gathering there. The result would be a large empty region surrounded by denser structures. These ideas are still being tested. Modern cosmology is filled with questions about dark energy, dark matter, and the precise conditions that existed shortly after the Big Bang. The Boötes Void might hold clues to those questions. Because when scientists look at a region this empty, they are not just studying missing galaxies. They are studying the limits of our understanding of how the universe formed. And that brings us to a thought that feels almost philosophical. When we look at galaxies, we see the bright parts of the universe. But when we study voids, we begin to understand the structure of space itself. The Boötes Void is not simply an empty hole. It is part of the architecture of the cosmos, a massive silent chamber inside the cosmic web. And in that silence, scientists may eventually uncover clues about the forces that shaped the universe long before the first galaxy ever appeared. As astronomers kept mapping the universe in greater detail, something strange began to stand out. The deeper the surveys went, the more the universe started to look like foam. Not random foam, a pattern. Bright filaments of galaxies forming thin walls, wrapping around enormous empty chambers. Those chambers are the voids. If you zoom far enough out, the picture becomes almost unsettling. Matter only exists along the edges. Everything else is darkness. The Boötes Void is one of the biggest chambers inside that cosmic foam. And once scientists understood that, the question changed. Instead of asking why the void is empty, they began asking something even deeper. Why does the universe arrange itself like this at all? Because gravity alone cannot easily explain the full shape of the cosmic web. Gravity pulls matter together, but the web shows long, delicate filaments stretching across hundreds of millions of light years, and those filaments appear too organized to be random. Cosmologists studying the structure of dark matter began examining this puzzle carefully. Dark matter does not emit light, but it dominates the mass of the universe. Galaxies form inside massive halos of dark matter. These halos act like invisible scaffolding where gas collects and eventually forms stars. To understand the cosmic web, scientists run enormous simulations that include dark matter physics. Some of the most famous simulations come from international collaborations involving the Max Planck Institute for Astrophysics and teams working with data from the Sloan Digital Sky Survey. Inside those digital universes, dark matter begins clumping almost immediately after the Big Bang. Filaments grow as gravity pulls matter along certain directions. Voids expand as matter drains toward denser regions. Over billions of years, the cosmic web emerges naturally. But when researchers examine those simulations closely, they notice something interesting. Voids often grow faster than clusters. Once a void forms, it tends to expand aggressively. The emptier it becomes, the less gravity exists inside it. That means the expansion of space affects it more strongly. In other words, voids can inflate like balloons. Galaxies near the edges slowly drift outward as the void grows larger. The Boötes Void may be a dramatic example of this process, a cosmic balloon that has been inflating for billions of years. But that still leaves one uncomfortable thought. If voids expand and merge over time, what happens to the galaxies that once existed inside them? The answer is not disappearance. Instead, those galaxies slowly migrate toward the edges. The process takes billions of years. But gravity from surrounding structures gradually pulls them outward. Over time, the center becomes emptier and emptier. That means the galaxies inside the Boötes region might not have vanished at all. They may have simply been relocated, pushed outward by the slow evolution of the cosmic web. Yet when astronomers try to track where those galaxies should have gone, the numbers do not perfectly add up. Some appear along the surrounding walls, but not all. There are still fewer galaxies than expected, even along the boundaries. That lingering imbalance keeps the Boötes Void slightly unsettling. Because the universe normally follows patterns that scientists can reproduce in simulations, but the Boötes region pushes those models to their limits. When astronomers observe the void using deep surveys and spectroscopic measurements, they notice something else. The few galaxies inside the void tend to be small and irregular. Many are dwarf galaxies. Some appear stretched or distorted in ways that suggest they evolved without much outside influence. Using detailed spectral measurements from the Keck Observatory and imaging data from the Hubble Space Telescope, scientists discovered that these galaxies often contain large reservoirs of hydrogen gas. Hydrogen is the fuel for forming new stars. In crowded parts of the universe, that fuel is quickly used up or stripped away through galaxy collisions. But inside the void, galaxies rarely collide. They live quiet lives, slowly converting gas into stars over billions of years. Imagine a small town far away from any major city. Life moves slowly there. Buildings change little over time. The same families may live there for generations. Galaxies inside the Boötes Void seem to live a similar existence, calm, undisturbed, but also incredibly lonely. And that loneliness leads to one of the most haunting realizations about cosmic void. If intelligent life evolved in one of those galaxies, their view of the universe would be completely different from ours. They would see almost no neighboring galaxies. The sky would appear nearly empty. The cosmic web itself would be invisible from their vantage point. Without nearby galaxy clusters to measure distances and motion, discovering the expansion of the universe might be far more difficult. Some cosmologists have even suggested that observers inside a large void might struggle to develop the same understanding of cosmology that we have today. In a strange way, the Boötes Void shows how much our own position in the universe influences what we can discover. We live in a region rich with galaxies. The Milky Way belongs to a local group of galaxies. Nearby lies the Virgo cluster, containing thousands more. Beyond that stretch enormous filaments linking superclusters together. We live in a busy neighborhood, but the Boötes Void is the opposite. A cosmic desert, a place where galaxies are rare and distances between them stretch across hundreds of millions of light years. The more scientists study this region, the more it becomes clear that voids are not just empty gaps. They are fundamental pieces of the cosmic puzzle. They shape how matter moves. They influence the growth of galaxies, and they may even hold clues about the earliest moments of the universe. But there is one final idea that pushes the imagination even further. An idea that some physicists consider when studying extreme cosmic structures like the Boötes Void. What if voids are not simply the absence of matter? What if they are regions where space itself behaves slightly differently? If that were true, the Boötes Void might not just be an empty bubble in the cosmic web. It might be a window into the deeper physics of the universe, a place where the balance between gravity, dark matter, and dark energy plays out in a way we are only beginning to understand. And if that possibility turns out to be correct, then the Boötes Void is not just a hole in the map of galaxies, it is a giant clue about how the universe truly works. If the Boötes Void is a clue about the deeper physics of the universe, then the next question becomes unavoidable. What exactly is space doing inside that enormous region? To most people, space feels like nothing, an empty stage where galaxies and stars move around. But modern physics says something very different. Space itself has properties. It stretches, it carries energy. It even bends when massive objects distort it through gravity. And on the larger scales of the universe, space is not calm at all. It is expanding. Every galaxy, every cluster, every filament in the cosmic web is slowly drifting away from every other one as the universe grows larger. This expansion was first discovered by Edwin Hubble nearly a century ago when he measured the redshift of distant galaxies. The farther away a galaxy is, the faster it appears to move away from us. That discovery changed everything. It revealed that the universe itself is stretching. But late in the 20th century, another discovery made the situation even stranger. The expansion is speeding up. Instead of slowing down under gravity, the universe is accelerating outward. Something is pushing space apart. Astronomers call that force dark energy. Dark energy is one of the biggest puzzles in modern physics. It makes up roughly 70% of the total energy in the universe. Yet no one fully understands what it is. It does not behave like matter. It does not cluster into galaxies. Instead, it seems to fill all of space evenly. And because it is tied to the fabric of space itself, its influence becomes stronger as the universe grows larger. This idea leads to a strange consequence. In regions where matter is dense, gravity can slow the expansion of space slightly. But in regions where matter is scarce, dark energy has less resistance. Expansion proceeds faster. That means the emptiest parts of the universe may actually grow faster than the rest. The Boötes Void might be a place where this effect becomes very noticeable. Inside the void, there is almost no mass to counteract the push of dark energy. The result could be a region where space expands a little faster than average. Over billions of years, that small difference would have dramatic consequences. Galaxies near the center would slowly drift outward. Matter would migrate toward the edges. The void would inflate like a balloon. If this idea is correct, the Boötes Void is not simply empty. It is actively growing, expanding faster than surrounding regions of space. And that could explain why the center remains so clean, with almost no galaxies left inside. Observational data gathered from galaxy redshift surveys support this possibility. Astronomers measuring the motion of galaxies along the boundaries of the void have found subtle velocity patterns suggesting that the region continues to expand. These measurements come from large survey projects and follow-up observations using instruments connected to observatories like Keck and spectroscopic studies recorded through Hubble telescope data. The motion is slow. On human timescales, it is almost impossible to notice. But over billions of years, the effect becomes enormous. Imagine watching the tide slowly pull water away from the center of a shallow pool. At first, the movement seems invisible, but if you return thousands of years later, the pool may be almost dry. The Boötes Void might represent that same process playing out on a cosmic scale. Yet even this explanation leaves a lingering curiosity. If dark energy can inflate voids, then the largest empty regions of the universe might eventually dominate everything. Clusters of galaxies would remain along thin filaments. But the spaces between them would continue growing larger. Over extremely long timescales, the universe could become a landscape of isolated islands surrounded by enormous oceans of empty space. Some cosmologists have explored this idea while studying the far future of cosmic expansion. If dark energy continues behaving the way it does today, galaxies that are not gravitationally bound together will eventually drift beyond each other's observable horizon. From the perspective of any given galaxy, the universe would appear to contain fewer and fewer visible neighbors. In an unimaginably distant future, each galaxy cluster could become isolated inside its own expanding bubble of darkness. When scientists think about the Boötes Void, they sometimes realize something unsettling. This enormous empty region might offer a preview of that distant future, a glimpse of what the universe could look like when cosmic expansion has stretched everything apart. But there is another thought that emerges from studying voids. Voids are not simply passive gaps. They influence the behavior of light traveling through them. When light from distant galaxies passes through large empty regions, the path it takes can change slightly. This effect is called gravitational lensing. Normally, lensing occurs when massive objects bend space and deflect light around them. But in voids, the opposite can happen. Because there is less matter inside, light passing through may experience a subtle shift. Astronomers studying distant galaxies sometimes measure these effects when analyzing the large-scale structure of the universe. Data from deep sky observations and large galaxy surveys help researchers map how light travels through these cosmic landscapes. Voids, including the Boötes Void, act like giant transparent windows in the cosmic web. They allow scientists to study how matter and energy influence light across vast distances. And in doing so, they may help reveal the true nature of dark energy itself. But despite all these insights, the Boötes Void still carries a certain eerie feeling. When astronomers look at it on the cosmic map, they are not just seeing emptiness. They are seeing a region where the universe's structure behaves in an extreme way, a place where matter drained away, where galaxies rarely formed, and where the expansion of space may be slightly stronger than average. It is a silent chamber in the architecture of the cosmos, a giant hollow bubble surrounded by walls of galaxies. And when scientists step back and look at the larger picture, they realize something profound. The universe is not built from galaxies alone. It is built equally from the spaces between them. The Boötes Void reminds us that emptiness is not simply the absence of matter. It is part of the design of the universe itself. But there is still one final possibility that some cosmologists consider when they stare at maps of the cosmic web. A possibility that sounds almost unbelievable at first. What if the Boötes Void is not just an extreme example of a cosmic bubble? What if it represents something deeper about how the universe began? Because hidden in the patterns of the cosmic web may be clues about the earliest moments of existence. Moments when space expanded faster than light. Moments when the entire universe changed shape in fractions of a second. And if those moments left scars in the fabric of space, some of those scars might still exist today. The Boötes Void might be one of them. If the Boötes Void is a kind of scar left behind from the early universe, then the story moves even further back in time, back to a moment when the universe itself was still forming its basic structure. Not stars, not galaxies, just space and energy expanding rapidly in every direction. Cosmologists believe that shortly after the Big Bang, the universe experienced a brief and violent growth spurt called inflation. During this period, space expanded faster than light for a tiny fraction of a second. That expansion stretched the universe enormously, smoothing out most irregularities while also amplifying tiny quantum fluctuations that existed in the earliest moments of time. Those fluctuations were incredibly small, but inflation stretched them across cosmic scales. What began as microscopic variations in energy became the seeds of the largest structures in existence. The clusters of galaxies we see today, the filaments stretching across the cosmic web, and the giant voids between them. Evidence for these ancient patterns comes from observations of the cosmic microwave background, the faint afterglow of the early universe. Space missions like the Planck satellite mapped that radiation with incredible precision. When scientists examined those maps, they saw temperature variations scattered across the sky. These variations correspond to regions where matter density was slightly higher or lower. Over billions of years, gravity magnified those differences. Dense areas pulled matter inward. Galaxies formed. Less dense areas lost matter to their surroundings. Voids expanded. In this picture, the Boötes Void may represent one of the largest low-density regions that formed in the early universe. But here is where things become interesting. Even the fluctuations observed in the cosmic microwave background rarely predict a void as large as Boötes. Most models generate smaller voids, usually tens of millions of light-years across. The Boötes Void stretches more than 300 million light-years. That difference raises a quiet question among cosmologists. Was the original density fluctuation in this region unusually large? Or did something else happen later that exaggerated its growth? Some researchers believe the answer might involve the merging of several neighboring voids. As cosmic time passed, smaller, empty regions expanded. When two voids touched, the thin filament separating them sometimes collapsed. Without that boundary, the two regions became one larger cavity. Over billions of years, repeated mergers could produce a giant supervoid. Computer simulations exploring this process show that large voids can indeed grow through mergers. In many cases, the interior of the combined void becomes extremely empty because matter has already drained toward the surrounding filaments. If the Boötes Void formed this way, it might represent the final stage of several voids merging together across cosmic time. But even this explanation does not fully erase the strange feeling the region produces when scientists study it. Because when astronomers examine the shape of the void, they notice something unusual. The region appears almost spherical. Most voids have irregular shapes, with jagged edges where filaments intrude. But the Boötes Void looks surprisingly smooth. That symmetry is difficult to explain through random merging alone. Some cosmologists have explored a more speculative idea. They ask whether certain phase transitions in the early universe might have produced large bubble-like regions with slightly different properties. During those transitions, the physical conditions of space may have shifted as the universe cooled. If one region underwent that change slightly earlier or later than the surrounding space, it could produce a bubble with lower matter density. That bubble would expand as the universe evolved. Matter would be pushed outward. Galaxies would gather along the edges. The interior would remain mostly empty. The result would look remarkably similar to the Boötes Void we observe today. Ideas like this remain theoretical, but they show how studying large cosmic structures can push scientists to rethink the earliest chapters of the universe. The Boötes Void is not just an astronomical curiosity. It is a puzzle that connects galaxy formation, dark matter distribution, cosmic expansion, and the physics of the early universe. And in that sense, the emptiness itself becomes meaningful, because the absence of galaxies tells us something about how matter moved through space over billions of years. It tells us where gravity pulled hardest, where dark matter gathered, and where the universe allowed emptiness to grow. But perhaps the most unsettling realization comes when astronomers step back and look at the bigger picture. The Boötes Void is enormous, yet it is only one of many voids in the cosmic web. Modern surveys suggest that the observable universe contains hundreds of thousands of these empty regions. Some are small, some are large. A few approach the scale of Boötes. Together they form a pattern that dominates the structure of the cosmos. Galaxies are the bright thread. Voids are the spaces between them. When scientists measure the total volume of the universe, they find something surprising. Most of that volume contains almost nothing. Matter collects along filaments and clusters, but the majority of space lies inside voids. This means the universe is defined as much by emptiness as it is by matter. The Boötes Void is simply one of the clearest windows into that reality. A region where the architecture of the cosmos becomes obvious, a place where galaxies are scarce and the vastness of space reveals itself without distraction. And when astronomers stare at maps of the cosmic web and see that giant empty bubble sitting among the filaments, they sometimes feel the same quiet question forming in their minds. If such enormous regions of emptiness exist between galaxies, how many more remain hidden beyond the limits of our surveys? Because the observable universe is vast, but it is still only a portion of everything that exists. Beyond the edge of what our telescopes can see, the cosmic web continues. Filaments stretch farther, clusters gather in distant regions, and voids expand silently in the darkness. The Boötes Void reminds us that even when something appears empty, it may still hold answers about the deepest workings of the universe. But the story of this giant cosmic desert is not only about the past, it also points toward the future. Because the same forces that created voids billions of years ago are still shaping the universe today. And over unimaginable stretches of time, those forces may continue pushing galaxies farther apart, slowly turning the universe into a landscape where vast empty regions dominate everything. For years, scientists tried to explain the Boötes Void using the normal rules of cosmology: gravity pulling matter toward filaments, dark matter forming invisible scaffolding where galaxies gather, cosmic expansion stretching the web slowly over billions of years. Those explanations work for most voids, but the Boötes Void keeps pushing the limits of those ideas. Because when astronomers run their best simulations of the universe, the results rarely create a region this empty and this large at the same time. A void 300 million light-years across should still contain hundreds of galaxies. Yet, inside Boötes, only a few dozen drift through the darkness. It is not just empty. It is almost completely cleared out. So researchers began exploring a final possibility. What if the Boötes Void is not simply the result of matter moving away? What if it is evidence that the universe itself behaved differently in that region long ago? Some cosmologists believe that during the earliest fractions of a second after the Big Bang, space may not have expanded perfectly evenly everywhere. Inflation, the rapid growth that stretched the universe into existence, could have created pockets where expansion happened slightly faster. If one of those pockets formed in the region that would later become Boötes, it could have produced a bubble with extremely low matter density. Over billions of years, that bubble would grow. Gravity would pull surrounding matter toward the edges. Galaxies would gather along the rim. The interior would remain almost empty. In other words, the Boötes Void might not simply be a gap in the cosmic web. It might be a relic of the earliest moment of cosmic history. A place where the universe expanded in a slightly different way than everywhere else. That idea is difficult to prove, but the evidence keeps pointing toward one clear conclusion. Nothing inside the Boötes Void actually vanished. The galaxies did not disappear, they were slowly moved, pushed outward by the combined effects of gravity, dark matter, and the expanding fabric of space. Over billions of years, that slow motion emptied the region until only a few lonely galaxies remained. The terrifying truth is simpler than it first appears. The universe did not erase 10,000 galaxies. It just moved them so far away from the center that the void became one of the largest empty spaces ever discovered. And that tells us something profound about how the cosmos works. On the largest scales, the universe is not built from matter alone. It is built from contrast. Bright filaments of galaxies surrounded by enormous chambers of darkness. The Boötes Void is one of those chambers, a vast, silent bubble where gravity drained matter away and the expansion of space stretched the emptiness even further. Today, that region drifts quietly between massive walls of galaxies. The few galaxies inside it continue their slow, lonely evolution, their night skies almost completely dark, their nearest neighbors unimaginably far away. But for astronomers studying the universe, the Boötes Void is far from empty. It is filled with clues. Clues about how the cosmic web formed. Clues about the role of dark matter and dark energy, and clues about the earliest moments after the Big Bang, when tiny fluctuations in matter density determined where galaxies would eventually appear, or where they would not. When you step outside at night and look up at the stars, it is easy to imagine the universe as a sky full of light. But the deeper truth is stranger. Most of the universe is darkness. Huge regions of space where galaxies are rare and the cosmic web stretches thin. The Boötes Void is a reminder of that reality. A place where the universe reveals its emptiness on a scale almost impossible to imagine. And somewhere out there, far beyond the limits of our current surveys, other enormous voids may still be waiting to be discovered. Silent, dark, and holding more secrets about how the universe came to be. If you want to keep exploring strange places in the universe like the Boötes Void, subscribe and continue with the next deep space investigation.